The last few lectures in this class are going to focus on energy resources, which is a topic you have spent the bulk of the semester working on via the modules and discussion. And I want to use today's lecture to introduce energy resources in a way that you may not have thought about them in the past. I think it's really important that everybody starts out when we talk about energy resources with an historical perspective of where we were and how far we've come, and the fact that very few people in the developed world want to regress and go back to a time when we didn't use energy the way we use it today. And I don't specifically mean the types of fuel that we use, but energy in toto. And certainly when we look around at developing countries, the more than 1 billion people on Earth who lack access to electricity and other forms of secondary and primary energy that on average we take for granted in the United States and other developed countries, I really think that it is our moral imperative to provide energy to our global residents to make sure that they have the access to opportunities that we do. So the question I'm going to start with is, why do humans harness energy from Earth? Something we don't think about. And I don't mean we harness energy to recharge our smartphone or to watch television or to illuminate our evenings when the sun goes down. But fundamentally, why do humans harness energy from Earth? It's because we can use that energy to do work either at times of the day when the absence of sunlight would not allow work to take place, or it's to do more work per unit time than humans can. So if we go back through history, there was a great story on NPR a few years ago, and I give you the link on the bottom. It's a great series, and I think it's a great episode if you want to listen to it, where economists have gone back and they've evaluated, to the best of their ability to do so with historical texts, how we used energy and how much that energy costs. And the time frame here, 2000 BCE, economists estimate that the average person working a blue-collar job all day, if you took your wages, you'd be able to buy enough light in the form of candles that you could have 10 minutes of light when you got home and the sun went down. And that was it. After 10 minutes, the candles would be extinguished and you'd have to work another day to earn a day's worth of wages to buy 10 minutes of light. And when we think about the types of energy we used, for example, animal fat. So for thousands of years, we would render the fat from animals, and you can see that here in the Pyrex measuring cup. And then we would allow that animal fat to harden, and we would dip wicks in that animal fat. And then we know that that animal fat experiences combustion when we strike a match and we light the animal fat. That gives us the flame here on this bottom right, medieval candle making. We've used fire for probably hundreds of thousands, if not millions of years. And I just want you to look at the video and listen to what I think is great music playing in the background. And I want you to think about what chemically is happening. I'm a big bluegrass fan, and I just love that video. And the crackling you hear is the water that's popping out of the wood when the wood is at high temperature. But when you see the flames, what do you actually see? You obviously see light. Intuitively, you know this is dangerous and you wouldn't want to get close to the flames because you know it would cause severe burns on your skin. But I want you to think about the energy resource that we're looking at. We're looking at a fossil fuel. In this case, we've got wood that's on a pile. That wood was previously alive. The wood is no longer alive because we have felled or killed the tree, and now we are combusting that wood. So I want to remind you of something you probably learned at some point long ago in middle school or high school. When we think about wood as an energy resource and a fossil fuel, which it is, we're talking about one of the end products of photosynthesis, where if we imagine a tree or any other living bush, or plant, as the one shown here in the photograph, right? The tree has its roots that go down into the soil, and those roots absorb water and other nutrients in that water. And the tree then, as sunlight strikes the tree combines water and carbon dioxide from the atmosphere and also from within air within the soil. And the energy is that sunlight, and that reaction that we call photosynthesis, water plus carbon dioxide plus energy, produces, in this case, glucose, which is a simple carbohydrate, C6H12O6. And that simple carbohydrate is the wood that we burn. And when we talk about a reaction the reaction combustion, what we're doing with combustion is we are lighting the wood on fire, our simple carbohydrate, in the presence of oxygen. And when that occurs, the carbohydrate reacts with oxygen and it gives off CO2 and water and heat. And that is the reaction that we know produces energy when we light a fire. So we start with that simple carbohydrate here top left. We add oxygen, which is always present in the air, and when you blow on a fire, if you've ever lit a campfire and you get down really low and you're really trying to blow the air closer to the fire, the oxygen in the air that stimulates combustion. And this is an irreversible reaction that liberates carbon dioxide, where carbon and oxygen used to be in the wood, and it liberates water, where the hydrogen was in the wood, and some of the oxygen from the wood and some of the oxygen from the air produce water and energy. And this is an exothermic reaction, meaning that more energy is produced than the energy it takes to combust. So combustion is an exothermic reaction, and we feel that if you've ever cooked a pizza in a wood stove, or you've ever put your hands around a fire. So this reaction of combustion, right, makes us who we are. So when we think of fire, fire is what allowed us to cook meat hundreds of thousands of years ago, which anthropologists think played a significant role in our brain's ability to develop at a faster rate than other primates. So combustion is a very basic reaction, and it describes how we use all forms of fossil fuel. So economists then tell us by the Middle Ages, so we fast forward from 2000 BCE to the Middle Ages, your blue-collar job would allow you to buy about an hour of light per night, 1 hour. So we've moved a couple thousand years, and we've gone from 10 minutes of light to 1 hour of light. Now, I'm going to use a figure that I'll unpack here, where I've got a timeline on the x-axis from 1775, the dawn of our country, the Continental Congress, through 2014, and I've got wood plotted here on the bottom. And on the y-axis is a unit of energy. And the unit here is quadrillion British thermal units. And a BTU is one of the ways that engineers define energy. All I want you to know is that quadrillion is 10 to the 15, so 10 with 15 zeros after it. And as we move from 0 to 5, 10, 15, we're talking about significant increases in energy. So all of the wood consumed within the United States over the last 240 odd years, all of that wood has liberated a total amount of energy per year that you see here on the y-axis. Right? So the fires that we've used to essentially build our country have liberated this much energy. So if we think about wood and animal fat and the candles that we made from animal fat and beeswax, which is another way that we make candles, I want to walk through now what I'm calling game changers for fossil fuel consumption. So we're not anywhere close yet to talking about solar panels or wind turbines or even yet hydroelectric power. We're talking about the game changers that allowed us to access the fossil fuels that were the low-hanging fruit intersecting the surface of the earth. And the first game changer was invented by a gentleman named Thomas Newcomen in 1712. He is credited with inventing the steam engine, and the patent that he applied for is stamped 1712. And many people think of James Watt as inventing the steam engine, but James Watt in fact took Newcomen's original design and he improved the steam engine, And the bottom left here is an actual image of one of the steam engines that would have been built in England around this time in the late 1700s. And when you look at it, it obviously, probably to everybody listening, looks archaic. And you're wondering, what does it actually do? What is the purpose of the steam engine? So I want to play you a video now, and I want to remind you of a comment I made a few minutes ago, that the reason that humans started using fossil fuels to the extent that we do now, and the reason that those fossil fuels powered the Industrial Revolution, is they allowed us to build machines that could do more work per unit time than humans. So I'll let this play through, and I just want you to watch it. So now let me walk back through it. Okay, so if we step back here and I pause it, I want you to see that humans invented this contraption or machine. And on the right-hand side over here, this arm and this arm are like a seesaw. So they're on a fulcrum in the middle, and just like a seesaw, you can see that they move up and down. Except when you're on a seesaw, you're on this side and you push with your legs so your side goes up, and then your partner over here pushes on their side so their side goes up, and the seesaw moves back and forth, up and down. Okay? So if you picture a seesaw, that's what I want you to think of, up and down, up and down. Now, here we're looking at a side view where the seesaw is out of the field of view at the top. And what we've got is we've got at the very bottom here a fossil fuel. And in fact, the first fossil fuel that Newcomen used was wood. So we have a fossil fuel here, and combustion is being used, so that carbohydrate is reacting with oxygen, and we have an exothermic reaction that produces carbon dioxide and water and energy. And then above that fossil fuel, we have a container of water, and as the video plays through, you can see the water is moving here. It's a rolling boil. So imagine you have pasta cooking on the stovetop and you've got the water at a rolling boil. Whoop. And you can see that here with the bubbles as they rise. And then those bubbles become steam at the top of the water column. And steam is more buoyant than air. It's less dense. So that steam rises up into this pipe. And within this pipe, this is a closed cylinder. And there's a piston right here that's attached to a cable. And that cable is attached to the seesaw just outside the field of view. The piston, when the steam enters this cylinder, the steam pushes the piston up, and that would be like your legs pushing the seesaw up. So the steam expands and pushes the piston up, and the piston is pushed up and pushes the seesaw up. And then at the very bottom, when the piston is at the very top, there's a pipe here that injects cold water. And that cold water cools the steam down, and as a result, the piston drops. And when the piston drops, the seesaw falls back on the left side, and the seesaw on the right is now at a higher elevation. So the piston is doing the work of the legs of a person on the seesaw here. It's moving the seesaw up and down, and up and down. This is Newcomen's atmospheric steam engine. And when you look at it, you might think, well, duh, it seems really simple. All it's doing is moving a piston up, and then the piston moves down, and the piston moves up, and the piston moves down. But remember, there's no human involved. There's no man, there's no woman, there's no child, there's no human, there's no animal involved. So there's no living creature that in any way is attached to the work being done. The work is completely the consequence of the combustion of this firewood, the fossil fuel at the bottom, which transfers that heat liberated by that exothermic reaction to the water. Water absorbs that energy, and when it reaches 100 degrees Celsius, it boils. That steam rises up into this cylinder where it condenses, pushes the piston up, cold water is injected, all of a sudden the piston drops, and this can go on 24 hours a day, 7 days a week, 365 days a year. It never needs a nap, never needs a break, never takes lunch, doesn't need coffee, doesn't need tea, never wants a sushi night, and never, ever stops working. So for the first time in recorded human history, yes, we used oxen to till fields. But now what we're doing is we're even eliminating the oxen and the horses, and we're letting the exothermic combustion of fossil fuels do the work for us. This was the first game changer, and this literally stimulated the Industrial Revolution. Because this is the first part of the industry in Industrial Revolution. Now, the next question is, why did we invent this? Well, on the right-hand side over here of this seesaw, you can see that it's on the left side we've talked about. On the right-hand side, this is actually connected at the base to buckets. And the reason it was connected to buckets is Newcomen invented this so that coal miners could artificially lower the water table, because just as we've talked about in previous lectures with big open pit mines, the coal mines in England at the time were open pit coal mines, and the coal was being used primarily as a source of heat in homes and office buildings. It was not being used for the Industrial Revolution yet, because nothing had been invented such as this atmospheric steam engine. So, where did the Industrial Revolution begin? Just some more history that you probably had a terrible teacher in 6th grade not teach you. But if you look at the whole map here, and I ask you the question, where did the Industrial Revolution begin? Where would you pick? Right? What country would you go to? Well, it turns out the Industrial Revolution happened in England, and it happened in England for a number of really important reasons. And I want to build on some of the material from previous lectures. So top right is a histogram where the y-axis is energy density. So this is something we talked about when Churchill decided to transition the British Navy from coal-fired to oil-fired ships, and oil has twice the energy density as coal. Well, when Newcomen and then Watt perfected the steam engine, they started by using wood, but then they noticed that coal had a much higher energy density, not quite a factor of 2, but depending on the energy, the grade of coal, it could be as much as a factor of 2, which means that for the same mass of coal that they put in their atmospheric steam engine, you could get as much as twice the amount of work. So now look at the image on the left. These are 19th century coal fields throughout England. All of these brown areas were coal that outcropped at the surface, meaning coal that you would trip over. Now, I said a couple of slides ago that a lot of coal, just like open pit mines that we've talked about before, if we look at the top here, we've got the water table that separates dry soil above from water-saturated soil below, what we call the zone of saturation. And what we find is that a lot of coal seams, if you look at them here left and right, they sometimes can exist above the water table, as these are, but then we can also have coal seams that exist below the water table. So what Newcomen designed his atmospheric steam engine to do is essentially to have buckets on one side of the seesaw, and those buckets would continually pull water up from below the subsurface that would allow the miners to artificially lower the water table so they could mine these coal seams below the surface. And this was a game changer for mining as well, because for the first time in human history, now mining could be done underground below the water table. So why did the Industrial Revolution begin in England, if you had to pick any country? We know that it started in England, and among the reasons is that England had what we today on some level take for granted, but we know are well codified in law, intellectual property rights and patent law. So there are fantastic books about this, and I highlight one here on the right, a classic book by Adam Smith called The Wealth of Nations, or the formal title, An Inquiry into the Nature and Causes of the Wealth of Nations. And when you read through the literature in the mid to late 1700s into the 1800s, and you evaluate the political and economic states around Europe and the rest of the world, at that time, Europe was the developed world. The United States was a nascent country. Europe was the developed part of the globe. In England, it was the only country in Europe that allowed individuals, you and me and your mom and dad and your cousins, you could ideate something, meaning you could come up with a great idea, you could sketch it out, and then you could file a patent that gave you complete legal rights to that particular thing. So what Newcomen did is he patented his atmospheric steam engine, which meant that anybody who wanted to copy his design had to pay him. And a lot of historians, they feel that this was critical for stimulating people in England to actually start inventing things following Newcomen's atmospheric steam engine, knowing that they could patent their own intellectual property rights. Some people suggest it was boredom. I don't buy that. There were lots of people bored around the world. I think it was the confluence of an unbelievably new invention that we didn't even know we were missing, kind of like our smartphone when Steve Jobs invented that. So we now have this new steam engine that's invented, and all of a sudden we have access to tons of coal at the surface to power the steam engine, and we can patent our intellectual property. So you put those together, and then what do we end up with? We end up with the Industrial Revolution. So on the right-hand slide over here, this is a schematic from the patent application that Thomas Newcomen put into the English government system in 1712. And notice on his schematic, I'll highlight over here, mine pump. His goal was to figure out a way to artificially lower the water table and allow mining to happen below the water table. And you can see on the left-hand side over here, that's what's happening. The piston goes down, and then when the piston comes up, it sucks water out from underground, and then it just empties it out onto the surface, or in this case, a bucket, but imagine that's the surface. So you put that together, and you look at towns in England, and again, you don't need to memorize any of the numbers, but all of these in brown I showed you are the coal fields. On the right-hand side, I've got coal fields in red, and then lots of the villages and cities that grew. It wasn't purely by chance. Manchester did not become an industrial city by chance. All of the areas of England that became major industrial powerhouses, they did so because they were located near coal. So if we focus in here on the area in central London, central England, here's Liverpool, here's Manchester, here's Newcastle upon Tyne. All of the brown are coal that you would trip over, and all of the black are the cities that grew during the Industrial Revolution because factories could be built close to the source of coal, meaning that geology played an incredibly important role at why cities in England developed where they did. So when we think about the Industrial Revolution, and again, just this theme of what it allowed humans to do, I'm going to play through parts of this video that I took at Mount Vernon a bunch of years ago. And I just want you to get a sense of when we buy clothing today and we think about how quickly clothing can be made by mass production in factories around the world. Let's go back a few hundred years. So Mount Vernon is where George Washington lived, first president.
My name is Melissa Weaver Dunning. I'm a master weaver, and I'm here at Mount Vernon today working on putting a new display on the loom here in the spinning house, we're putting on a relatively coarse linen that is similar to the fabric that might have been used for shirts that were given to the slaves, 1 shirt per year. And we have wound the warp, and which is measuring it out on a large board. We beamed it, rolled it onto the loom itself, and then threaded the heddles, which are these strings here. Each thread has to go through a little thread eye, which is kind of the long and tedious part. And then we thread the reed, which separates the thread and lines them up. And then we got it all tied up and we're ready to weave. So this type of loom is a loom that was commonly used for several hundred years in Europe and then in the Americas. This particular shape of loom would have been called a four-poster because there's, like a bed, a post at each corner, and the seat is attached. Sometimes they were separate. These today are sometimes called barn looms, but we think that's mostly because people stored them in barns. The people who used them would not have called them barn looms. And it's probably about 200 years old. One of the most interesting things for me about this loom is that the way it's constructed shows it to be a linen loom. The framing of the loom that helps the support is right on the ground rather than up 6 or 8 inches. And what that allowed the weaver to do is, working in a room with a dirt floor, they would have thrown 1 or 2 buckets of water under the loom to create a more humid environment for the weaving linen. Here in Virginia, at least in the warmer months, we don't really need to add humidity. But particularly in the winter, that would have been very important. So we know this was a linen loom.
So I'm going to stop it here. And again, the point of me showing this video to you is just to take you back 200 plus years and imagine how painstaking this was. She started off, first of all, by mentioning and using the word slave, and slaves would have been given 1 shirt per year. We know that George Washington and at least 6 of the first 8 to 10 presidents owned slaves, and slaves were responsible for building the White House itself. So this is how they would have sewn shirts. After the Industrial Revolution, when all of a sudden humans had access to the power of fossil fuels, look at the bottom left, okay? Here we've got bottom left and top left. All of a sudden now factories were built where instead of one person doing what the woman in the previous video did at Mount Vernon, which by the way is a great place to visit. If you ever go to Washington, D.C., you should go to Alexandria and spend at least half a day at Mount Vernon and walk around the grounds and tour the house. It's a fantastic place to visit, looking out on the Potomac River. So if we then think about industrialization, now look what happens. This is the result of the steam engine. So what's different in this video? I'll just give you a hint here.
My name is...
Take a look here and take a look here. There's no human, right? After the Industrial Revolution, what is the Industrial Revolution? It's eliminating the need for as many humans as we previously used, in this case, to make cloth or fabric, which we're using to make shirts. So that simple invention by Thomas Newcomen and then perfected by James Watt, where we're using fossil fuels, that stimulates the Industrial Revolution. And for humanity, all bets are off because everything changed when in England, individuals could file a patent for all of the equipment you see here in these photographs, and all of a sudden, humans were required to do less work, and we could be repurposed to do work differently. And so the Industrial Revolution starts in England up here in the 1840s, and then we see it just proliferates across Europe. Now, if anybody in the class is interested in law and legal history, there are also lots of great books written about the intellectual property rights on continental Europe across into Russia and why they really worked against individuals ideating new things because there was the absence of patent law. So we have this spread of the Industrial Revolution, and then it works its way around the world. So another great place to visit, if you ever go to Baltimore, on the campus of Johns Hopkins University is the Baltimore Museum of Art, and this is one of my favorite paintings. It's from the 19th century, 1868, by Frank Blackwell Meyer, and you can read the caption. The leather-aproned blacksmith was a potent American symbol of noble handcrafts during the increasingly mechanized 19th century. His tools lie idle, and his anvil is nearly covered by an open newspaper, that all-important vehicle for mass dissemination of information. So when I mentioned humans were repurposed, prior to the Industrial Revolution, blacksmiths made everything metal, and the Industrial Revolution allowed humans to create or invent machines that made that metal for us. And it put blacksmiths out of work, because if a machine could do the work of 10 men in the same amount of time, why would you hire 10 men to do that work? You would hire no men, you'd have a machine, and you would allow the machine to operate 24 hours a day, 7 days a week, 365 days a year. So then what happened? The next game changer is transportation. So on the bottom here is a photograph where the body of water running through the center is the Erie Canal. And the map on the top, this is Albany, New York on the right-hand side, Troy, New York, and then south would be New York City, give or take 2 hours. This is the Erie Canal in black that was dug by hand across New York, connected Syracuse, went across through Palmyra, Rochester, New York, across through Albion, all the way across to Buffalo. And the Erie Canal was originally built so that goods from the Midwest could be shipped across Lake Erie, put on the Erie Canal, and then pulled, because they were put on barges, and they were pulled by horses or oxen all the way across New York, where they could be put on ships on the Hudson River to New York City, and then goods could go the other way as well. So this is a photograph of cargo being pulled on a barge on the Erie Canal, and you can see here we've got the cargo on a barge connected by a rope, and we've got 3 horses, and we've got somebody behind the horses here, and the horses are pulling this cargo. So just imagine how long that would take you, right? We're literally talking about walking across New York pulling cargo. Now, it was faster than any other route of transportation because there was no other route of transportation apart from walking in the absence of water. So what we're using here is the ability of water to hold up the barges to make it easier for the animals to pull. And this is how we transported goods. So the Erie Canal, which was begun in 1817 and finished in 1825, this is a snapshot here on the lower right of how we used to transport apples. Apples would be picked in upstate New York. They'd be put in barrels. The barrels would be put on barges, and then they would literally be floated via the Erie Canal across to Albany, and then they would be floated downriver to New York City. Then we had another game changer, and that was locomotives, or what we think of as railroads. And those railroads were powered by coal. So coal is what was responsible for starting the Industrial Revolution in England. And once humans ideated and built coal-fired locomotives where we have an engine up front, notice the steam is coming out. These wheels on a train, they move using essentially the same design as Thomas Newcomen's atmospheric steam engine, where we use coal and we combust coal by adding oxygen to it. It's an exothermic reaction that liberates energy, and inside the locomotive we have a piston going up and down and up and down, and just like the piston moved the seesaw on the atmospheric steam engine, it moves the wheels, and the wheels propel the train. And on the map here, I've got, or the map shows us, the major railroad lines from the East Coast to the Midwest, and this is the railroad lines for the B&O Railway, the Baltimore and Ohio Railroad Company. Here's Baltimore here, and the railroads were built to move west, and you can see that they eventually moved west out into Ohio, up into Michigan, Toledo, Detroit, Gary, Indiana, and Chicago, and this accompanied westward migration in the late 1800s. It allowed faster movement of people, it allowed faster movement of goods, and if you look, this is just a manifest showing the amount of coal that was moving. You can look at this in more detail, but Frostburg is in western Maryland, and so we're talking now here about other railways moving goods and services much faster and over much greater distances. And again, they could operate 24 hours a day, 7 days a week, 365 days a year. Unlike horses, you didn't have to let them rest. You didn't have to feed them except for providing coal, and you didn't have to allow them to take breaks during the day. And if you ever play an original game of Monopoly and you look at the railroads, at the time we've got the B&O Railroad down here, we've got the Pennsylvania Railroad up here, the Reading Railroad, and the Short Line. The B&O Railroad was one of the most valuable companies on planet Earth. It was at that time the Berkshire Hathaway or the Facebook or the Microsoft, because B&O Railroad controlled all of these arteries throughout the East Coast and into the Midwest, as far west as St. Louis. And so what we're seeing here is railroads displacing not only canals, but also displacing transport on rivers. So the second game changer, okay, was electricity. So coal is the first game changer. The second game changer is electricity, and coal will play a part. So anybody who remembers Benjamin Franklin, one of the founding fathers of the United States of America, instrumental in helping draft the documents that allowed us to become a free country and leave the control of England. Franklin conducted a famous experiment with a kite and a metal wire and a rod, and all I want you to take away from this is that what Franklin was able to do is he was able to deduce from his experiments that lightning is electric current. And this was essentially the discovery, as we now give him credit, for electricity, because that electric current, when it flowed down the string, gave him a shock. And that convinced Franklin and others that it represented a current that moved through air along this wire, and that stimulated other people, such as Thomas Edison and Humphrey Davy before him, to invent the first electric light. And they did that because they could see electricity, they saw that as energy, and they saw the ability to harness that energy and have it flow through material. So Humphrey Davy, he built the very first light bulb in 1802, and then others, including Edison, who is credited with perfecting it, they continued to build electric lights. And notice the very first one lasted only 13 and a half hours. But 13 and a half hours could get you through an entire night or through a long afternoon and evening if you wanted to operate a second shift at a factory. So what do you need if you want to have electric lights? You need electricity. So Edison and his partners also, they were responsible for building the first coal-fired electric power plant. On the left-hand side is a photograph of the first electric power plant, or the building that housed it. And they did this in 1882. The first one was in London, England, and then they built one in New York City. And how they did that was, instead of using wood, just like the English for the Industrial Revolution, they used coal. Coal is carbon. When you add oxygen to carbon, carbon plus oxygen is an exothermic reaction when you give it a spark, like a match, and that liberates carbon dioxide as a byproduct. And it also liberates energy, and you can see that energy here is the fire. And in coal-fired power plants, I'm not going to go through the details here, but just accept that coal is used, and ultimately we have electricity come out of the coal-fired power plant. So this was a game changer. And when the world saw this image on the bottom left, everyone wanted electricity. So we used to have around the world what we would call world expositions or world fairs. In 1893, the world's Columbian Exposition was held in Chicago. And on May 1st, 1893, President Grover Cleveland opened up the Grand Exposition. And what he did was, after the sun set, he flipped a switch and instantaneously electricity flowed through metal wires and illuminated 100,000 incandescent light bulbs. So we went from the first light bulbs being invented in 1802 to less than 100 years later, Grover Cleveland instantaneously illuminating all of this area of Chicago, which even in black and white, immediately when this went around the world and was published in newspapers, everyone looked at this and said, I want that. And to get that, we started using coal. So now we're back to the same plot I showed earlier with our quadrillion British thermal units on the y-axis and time on the x-axis from 1775 until 2015. Wood is here that we saw earlier, and now look what happens with coal. So here we are, 1893, the World's Fair. Edison invents the first coal-fired power plant about here, early 1880s, and our appetite for coal took off. Now there are some ups and downs in here that I'm going to ignore for this class, but I just want you to see the trend, which is this incredible increase in our use of coal to generate electricity and to power locomotives for the purpose of transportation. And if we fast forward to the end of the 19th century, economists tell us that because electricity and energy is now getting cheaper, 1 day's of wages could buy 1 day's worth of electricity. So if you lived in Ann Arbor, and this is a photograph of our railroad depot in 1890, in 1890 we still had no vehicles that we think of as we have today, no battery electric vehicles, no combustion engines. Everything was horse and buggy, but you could work for a day and you could buy enough energy to last 24 hours. So what was the next game changer for fossil fuel consumption on an industrial scale? Imagine in the 1800s, you were a farmer and you were threshing grain. So think of wheat, and we're threshing it here for the purpose of making flour to bake bread. With only manual labor and manual tools that you see in the photograph, it would take 25 men a full day from the time they got up in the morning until the time the sun set to harvest and thresh a single ton of grain. So think 25 men, 1 full day, 1 ton. And then what happened? I'm going to play you a video of the next game changer.
Science, please! Do the words auto mechanics make you curious? Actually, it's a cinch. A car is made up of wheels, seats, fuzzy dice, a body, and an engine. The internal combustion engine. The engine works in 4 stages. First, a valve opens and the piston lowers, letting a mixture of fuel and air into the combustion chamber. Second, as it comes up, the piston compresses the fuel-air mixture. Third, a spark from the spark plug ignites the mixture, which pushes the piston down again. Fourth, the exhaust valve opens, and as it comes up, the piston pushes the spent gases out. And the cycle starts over again. Intake, compression, combustion, exhaust. Intake, compression, combustion, exhaust. Intake.
This is the combustion engine that most of us are familiar with. When we put gasoline or petrol into our engine, again, what are we looking at? A piston that goes up and down and up and down and up and down. And what causes it to go up? It's the combustion of a fossil fuel. And that fossil fuel in this case is what we call isooctane, which is a component of oil that I'll talk about in a future lecture. And isooctane, when it mixes with oxygen, which in that video is the air intake, mixing with isooctane, which is the fuel that you pump into your gasoline tank, that is an exothermic reaction that produces carbon dioxide and water and generates lots of energy. So again, a combustion reaction where humans are using a fossil fuel, in this case oil, and I'll explain why that's a fossil in the next lectures. By combusting that with oxygen, we produce energy, and that allows us to do more work than humans could do. And this is the example. So in the previous slides, I said it took 25 men a full day to harvest and thresh a ton of grain. If you look at the photograph on the right, this is what we call a large combine, and it is, as it moves across the field, it is harvesting and threshing grain, and then it is shooting that grain up into a second truck here, and they both are controlled by GPS. They both are controlled by cruise control, and in 6 minutes, one person in a GPS-guided combine, you can almost see the legs of the person sitting here, one person can harvest and thresh a ton of grain in 6 minutes compared to 25 men taking an entire day to do this prior to the invention of combustion engines. So again, the theme here is we're harnessing energy in the form of fossil fuels to do work faster than humans can do it. And it's not just faster, it's much faster. So we credit Henry Ford with inventing the mass production of the automobile, and that happens here in the very early 1900s. And as a result, if we look at human consumption of oil, and petrol or gasoline as we know it is a byproduct of oil, look at our consumption of oil. It overtakes coal by World War II, and then it just continues to climb. We have a couple of drops here. We had a OPEC crisis in the early 70s, another oil crisis in the early to mid 80s. We continue to see it climb. This is dropping oil after the last global recession in the late 2000s, and oil has continued to climb except during our current pandemic where we see significant drops in oil. And again, I showed you these photographs earlier in the semester. In 1900, there's one combustion engine in the photograph, and that's right here, no horses. Everyone else is on a horse and buggy. And by 1913, everyone's driving a combustion vehicle. You could get there faster, and so faster was better. You could have more people in the vehicle than you could on your horse and buggy. You didn't have to water it. Now you had to add gasoline and you had to add water to the radiator, but otherwise it was a significant leap in terms of efficiency over travel by horse or foot. And we see this recorded in any number of ways. So on the bottom here we've got time, roughly 60 years beginning in 1900. The red here are the number of horses and mules that we used for farming, and you just see them drop. And then you see the number of tractors just continue to increase. And so again, we mechanized farming. And I know that there are many people, and in fact some of you in the class may be opposed to mass agriculture. So I'm not saying that this is right or wrong or good or bad. This is the observation we can make as we saw the transition from manual labor to mechanized labor. And we see this repeated over and over and over again. We invented suburbs, and we invented the concept of grass only for the purpose of mowing grass on your day off, which to me is among the silliest human inventions of all time when you think about the amount of land here that we could grow food on. But we'd rather cut the grass, and then we do other silly things. So the next fossil fuel that we start using en masse is natural gas, and that's shown here. I'm tracing over with the cursor. And natural gas, we start using it around World War I, and natural gas becomes a favored way to generate what we called town gas or illumination, and also we use that to generate electricity. In the early 1900s, we also started building hydroelectric dams. So I showed you in a previous lecture the Hoover Dam outside Las Vegas, and here we have hydroelectric at the bottom. And I'll come back and talk about the details of hydroelectric in a lecture next week, but I just want you to see that hydroelectric has effectively plateaued over my lifetime and your parents' and grandparents' lifetime for reasons I'll get into. Then we see nuclear, and nuclear is a byproduct of the Manhattan Project that we in the United States operated during World War II that allowed us to develop initially the nuclear bomb, and then we were able to harness nuclear energy for the purpose of nuclear electricity, which is shown here. And nuclear electricity, that has also plateaued. If you saw Chernobyl and you're aware of Fukushima and 3 Mile Island, the social license to build new nuclear electric plants in the developed world has effectively gone to zero. And then we see renewables down here on the bottom. Now, it's important to highlight that renewables, if you look here at the lower right, they have grown significantly in your lifetime, but I want you to take the whole picture in here holistically. If we go back to 1775, we used wood, we used animal fat, we used beeswax. And then if we work our way through the last couple hundred years, we see this significant growth in coal and oil and natural gas. We see a small amount of hydroelectric compared to these fossil fuels. We see a relatively sizable amount of nuclear electricity, because the only thing right now we harness nuclear power for is electricity. We also use it for defense applications, for example, the nuclear-powered naval fleet, submarines, and battleships. Renewables are down here, and when we think about a world where we divest from fossil fuels, that would be a world where renewables, which right now are at about 5 times 10 to the 15th BTUs for the United States, they have to climb and exceed the sum of the energy output from oil, natural gas, and coal. All three have to be replaced. Now, just a few other things to tie into this, just to make sure that when I make comments, such as I did at the beginning of this lecture, that I've not yet met anybody who wants to go backwards in time. On the right-hand side over here are a range of different countries, including the United States. And I just want to take you through a timeline of percent electrified. If we go back to the early 1900s, nobody had electricity. Right? It was a rarity. There were a few lucky people that had it in places like New York and London. And then what we see in each country, here's the United States, is we see this year-over-year increase in percent electrified. And what we can now see around the world, there's a lag time for other countries, is that each of these countries has either hit 100% electrified or is on its way to 100% electrified. Not all countries have gotten there. Among them, India, depending on whose statistics you believe, India has as many as a few tens of million to a few 100 million people who lack electricity. Now, why is electricity important? Because one of the observations that we make is as the percent electrified increases, or restated, as the access to electricity increases for residents of any particular company, the average income increases. And so we see economic empowerment, economic improvement increase as we electrify and make access to electricity the norm in countries around the world. And this is our world now.
In daylight, our big blue marble is all land, oceans, and clouds. But the night is electric. Seen from space, our planet comes alive with light. This new view of the Earth's night lights is a composite of data acquired by the polar orbiting SUMI NPP satellite. Aboard the satellite, a newly designed instrument called VEERS is able to collect what scientists say is a remarkably detailed view of the Earth at night. In some places, city lights resemble solitary stars in the night sky. In other places, dense clusters of galaxies. The satellite can even distinguish brightly lit boats that line Egypt's Nile River, and the massive flames from gas flares produced as a byproduct of oil and gas exploration in the Middle East. As the satellite passes over the darkness of the Himalayas, it shows how human settlement is bound by natural borders. Even political borders are starkly visible in this view of North and South Korea, and in a line of fishing boats that dot the Yellow Sea. But not all light is electric. Glowing just as bright, flaming wildfires burn across Australia. This new view of the Earth at night offers a unique perspective for exploring the many places in which we live and seeing the impact of human populations around the world, no matter how faint or how bright their lights shine.
So this to me is an amazing look at our world, and I just want to highlight a couple of things. You know, this is the Nile River in Egypt, and these are fishing boats, all at night, and we know that they're fishing boats because they're all illuminated and they're all floating in the water. And then we move up towards northern Egypt here into Alexandria and Cairo. As we move across other parts of the world, we see in the Middle East, all of these flares here, these are natural gas that is being flared off during oil production. As we look at India, we see the Himalaya Mountains to the north and the Tibetan Plateau. We can see India with 1.3 billion people and neighboring Pakistan. And notice all of the lights here that are an indication of all of those people. And then when we get into the Himalaya Mountains proper, we see the absence of light reflecting the absence of people. He mentioned the Korean Peninsula, which again is stark. So here we have Japan on the right, we have South Korea here, this is North Korea. And what the light is telling us is that South Korea is glowing at night with an economy that runs 24 hours a day, 7 days a week, 365 days a year, and North Vietnam is economically the exact opposite, up here with no lights except for a very faint glow here. And then we also see in China, those cities I talked about on the East Coast, Beijing, Shanghai, right? We talk about pollution transfer as we move factories, the global we, from Eastern China further inland. So we've come a long way in only a few hundred years, right? Here's the U.S. night skyline. We can pick out Chicago, Detroit, Cleveland, Toledo, right? These are all cities that jump out at us. Chicago, Detroit, Cleveland, Toledo, right? Over here is Buffalo. We've got Long Island, looks like a flashlight. New York City, Boston and the surrounding areas. Up in northern New York, we get to Montreal, Ottawa, Canada, Toronto, Canada, right? We can move across the country, and what we see at night is an indication of how radically our worlds have changed in a very short amount of time. And today, if you look at the actual cost of electricity, if we think of that form of energy, we can buy thousands of hours of energy, whereas throughout almost all of recorded time, human time, we could barely afford to illuminate our nights for minutes to hours to a day. This is perhaps one of my favorite graphics that I came across in a book a few years ago. And I want to walk through it just again to give you some historical context. It's simpler than it seems. The x-axis is time from 1890 through 2015. The y-axis is the hours of household work per week. So imagine your household, all of the things that you had to do in your household to maintain your home, the cooking, the cleaning, etc. If we go back 100 years, the average number of hours of household work per week was about 60 hours. Now this was outside of other work you might be doing. This was to keep and maintain your home and have a garden and take care of yourself on your plot of land. Notice that that housework over time, if you follow my cursor, has dropped and dropped and dropped and dropped and dropped and dropped. And it's now about slightly less than 20 hours a week of housework. Okay? Now, how could housework drop? Well, the reason housework dropped is We invented electricity. That's our invention. We harnessed the power of fossil fuels to produce electricity, and electricity allowed us to do many things. It allowed us to build water systems, which I admit are not perfect everywhere, certainly if I think about the citizens of Flint, only an hour north of Ann Arbor. But electricity allowed us to develop running water and also wastewater. Think about what happens when you flush the toilet, or you take a shower, or you run the dishwasher. Where does that water go? It just disappears, and magically somebody takes care of it, and electricity is responsible for that, or partly responsible. We invented the refrigerator, the vacuum cleaner, the washing machine. So here we have the washing machine, which we invented. And notice that washing machine now is in about 85% of homes around the country. We invented the dishwasher. So all of these are inventions, just like Thomas Newcomen's atmospheric steam engine. And all of these inventions allowed humans to do work faster per unit time. The microwave is one that I tell my kids. I remember when my mom got our first microwave about 1985. And initially it was incredibly simple. It had a dial that you simply turned on, and then all it did was operate at one speed. That's it. And then we invented things like microwave popcorn, which became a thing in the 80s. But notice now almost everyone in the United States has a microwave. And how many people who are listening to the lecture, when you want to heat something up very quickly, what do? You just put it in the microwave. How does the microwave work? It needs electricity. So I'm not assigning a good and a bad, a right and a wrong. These are the data that we have, and they allow us to make the observation that as humans have invented machines to replace manual labor, those machines require electricity, and electricity requires fuel, and the fuel that we have depended on since the Industrial Revolution has been dominated and is currently still dominated by fossil fuels. So when we look at the United States, and this is the same plot I showed you a few minutes ago, one of the challenges, and I touched on this earlier in today's lecture, is that we as a country are 5% of the world's population. So this is for the United States in specific. We're 5% of the world population and 20% of world energy consumption. And one of the things that we are challenged to do as a global society, and certainly as members of the United States, we are challenged to figure out how do we replace the fossil fuels with so-called renewable energy resources such as solar and wind and perhaps nuclear and perhaps more hydroelectric. And how do we actually reduce our share of world energy consumption so that people elsewhere around the world have access to what we have access to today? Because when we look at all of these machines, it doesn't make us bad people. It makes us the people we are. And when I visit countries in the developing world, I will tell you everyone wants access to what they see us having access to on a daily basis. So last few slides, you looked at something like this way back when for Module 1, and I just want to make an important point here because I think the media almost always gets this wrong. When we talk about energy, we talk about primary energy consumption and secondary energy consumption. And this was for the year 2018, and it's effectively unchanged for 2019 and 2020. If we look at the U.S. primary energy consumption, 31% natural gas, 36% petroleum, and petroleum here I mean oil or crude oil and its byproducts, 11% renewable, and renewable is divided here among different types of renewable, including hydroelectric, wood, biofuels, biomass waste, wind, solar, and geothermal, about 8% nuclear, and all of that nuclear is electric, and about 13% coal. Now, what I want you to take away from this pie chart and the concept of primary energy is that this is all of the energy used for planes, trains, automobiles, air conditioning, heating, lighting, microwaving, hot water, you name it. So we use a phenomenal amount of primary energy, And some of that primary energy is used to produce electricity. One of the things that some of the members of Congress got wrong when they proposed the Green New Deal is they didn't understand the difference between primary and secondary. And secondary energy is electricity. So again, this is just another snapshot where I want you to see the amount of primary energy that we've consumed since 1950 through 2018. I highlight up here 2018, we consumed more energy in the history of the United States. And again, all of this is primary energy. You don't need to memorize the proportion over here, but I want with words to make sure you understand primary energy is all the energy we consume. And when we talk about electricity, that is a secondary form of energy because we're using primary energy to generate electricity. And it turns out that electricity is a small part of the overall energy that we consume. So here's where we are, and here's what I've had you work through on your modules. And I really pray that the modules, you found them interesting. I know that the writing can be a pain in the ass sometimes, but I hope you were able to just push through that. What I really hope you were able to do with the modules up through module 7 as of this week, and next week you'll do modules 8 and 9 to look at costs and resources, is we have an energy infrastructure today where this is the common scene bottom left. We're pumping petrol into a car, and that petrol comes from crude oil. We're generating electricity using uranium in power plants, using natural gas. We're heating water with natural gas. We're cooking with natural gas. And then we're plugging into coal to generate electricity. And we have these massive power plants, like those that are shown here schematically, and all of these electric lines that bring that power to our homes. If we imagine a world where we can put an X through all of these power sources on the left and we plug in our Teslas, wouldn't it be nice if everybody had a Model S? And we power all of our energy resource needs from renewables such as solar and wind and hydro and possibly biofuels. That requires replacing a lot more primary energy than what the media commonly lead you to believe. So the last couple of slides, why do we want to do this? I'm not going to give a lecture on climate change in this class. I will tell you that the climate doesn't care how you vote, doesn't care who you pray to or if you pray. The climate is changing because of those irreversible combustion reactions that I talked about in today's lecture. Carbon plus oxygen produces CO2. CO2 is a greenhouse gas. As the atmosphere increases in greenhouse gas abundance, that greenhouse gas traps heat, and that trapped heat causes temperature to rise. This is a really simple chemical reaction, and I have not yet met anybody of any political persuasion who can demonstrate to me that that is not a fact. But for political posturing, we now have one party that disavows themselves from that fact. So, how do we relate fossil fuels and combustion of fossil fuels to climate change? When we look at the data here for all of the fossil fuels that we've combusted over the last 200 and some odd years, we know that combustion of coal produces CO2. We know that combustion of oil produces CO2. We know combustion of natural gas produces CO2. We know combustion of wood produces CO2. This is like a no shit, Sherlock. These are Wikipedia facts that I can tell you you learned in elementary school and middle school and high school, and again, no one can disprove them. And here in red, I've calculated and overlaid on top of the fossil fuel consumption data. The red here is all of the carbon, which is shown on the scale on the right, all of what I call here the anthropogenic carbon, meaning human carbon, that we have released to the atmosphere as a result of combusting the oil and the coal and the natural gas. And we know that as the amount of CO2 in the atmosphere, here measured as carbon, which is really relatively easy to calculate because we know how much coal and oil and natural gas we've combusted over the last 250 years. We know that that has led to the hockey stick that I showed you here. So I'll leave you with that. And what we'll do over the next few lectures is take a high-level approach at each of these different types of energy resources, just to give you a sense, a little more understanding of how they form geologically, how we use them, and why all of these fossil fuels are finite, and if only because they're finite, that is the reason to transition to renewables. The second reason, as you'll learn in Module 8, is renewables are much cheaper.